Okay, so uh, here is the title. It's quite long, but what we are really going to talk about is that scary 1.7 terabit DDoS attack. Let's first start with some definitions. So, what's an amplification DDoS attack? In a nutshell, most servers on the internet serve data to clients, and they usually send more data to a client than they receive from them. This is okay for TCP-based servers, as the TCP protocol has a built-in mechanism called triple-way handshake, and it was used by Daniel J. Bernstein back 20 years ago to verify the remote IP address of a client. So in TCP, you can just spoof a lot of TCP connections. However, there's no such mechanism present in UDP, and each author of a UDP-based protocol must design their own handshake, and sometimes they just omit that in a design phase. Modern protocols like QUIC, designed by IETF, implement proof of ownership, proof of source IP address ownership with different methods. Like in QUIC, first, the initial handshake packet is padded to almost 1,300 bytes to make sure that the server wouldn't be able to send more or much more than it has received. Also, during the handshake, the source IP address of a client is validated. So with modern protocols, most of the time, it's more or less okay. However, for much older protocols, there's no such handshake present in a protocol specification, and an attacker is able to impersonate a victim by spoofing source IP address and to send a request for a large portion of data on behalf of the victim. An attacker will generate, say, 1 gigabit of requests, but the victim will receive, say, 30 gigabit of responses, which may impose serious consequences for the link congestion. There's a long list of protocols vulnerable to amplification. Those are mostly obsolete protocols, as we've discussed before, like Routing Information Protocol version 1. But there are also modern protocols, such as gaming, like Quake or Steam protocol. As it's mostly obsolete servers, they eventually get updated or replaced or just trashed. Thus, the amount of amplifiers shows steady downtrend. However, once in a while, a new vulnerable protocol is discovered, and the number of amplifiers on the internet skyrockets at that moment and then starts to decline again. The amplification factor is how much data you can get in return towards the victim from an amplifying server compared to the size of the original request. There's also a stable downtrend in terms of available amplification power. The factor is quite different for each protocol, like NTP, network time protocol, being 10 times more powerful than LDAP. Yet, most amplification attacks are easy to fight with, as the source UDP port is fixed. So at first glance, you can just use a simple bit mask to track down and filter packets which come from a typical amplification port. Moreover, there's a mechanism you can use to actually order that filtering from your upstream connectivity provider. It's called flow specification rules, RFC 5575. Using flow spec, you can notify your upstream provider or your peer that you don't want to receive, say, packets from a particular UDP port, like 123, which is NTP, which comes in handy when you face a powerful amplification attack. However, there are at least two major problems with flow spec for that particular task. Unfortunately, flow spec isn't a silver bullet here. The first problem is ICMP amplification. If you use flow spec to drop all the ICMP packets, this will have serious consequences for other protocols and network interoperability. System administrators which drop all the incoming ICMP traffic are described in the IP tables man page as brain dead, and that's for a reason. So you don't want to do that. And the other problem is when an amplification attack doesn't actually have a fixed UDP part. One example of this used to be WordPress pingback. During the pingback DDoS, an attacker forces a vulnerable WordPress installation to issue HTTP or HTTPS requests towards a victim. WordPress is the most popular CMS in the world. So with literally millions of those installations available on the internet, an arbitrary attacker is practically capable of generating a few gigabits of just thin TCP segments using this method, and up to a few dozen gigabits of a total attack. As the WordPress installation starts a new request itself each time, the source port is always different. And flow spec is of no help to us. In case of TLS-enabled resource, the only information enough to reliably tell a WordPress server from a legitimate user is encrypted. There's also a different problem, like flow spec consumes resources, and network operators usually hate giving capability to export flow spec rules to anyone. Here, I'll take an opportunity to point you at the presentation by Benedict Rudolph from DETEX tomorrow and at 2 p.m. about deploying flow spec with bird routing daemon, and how does the latter perform under different worst-case scenarios. So anyway, pingback was the first case of web development causing denial of service problems, including those that couldn't be easily handled with flow spec to ISPs. With that, let's proceed to the February's hero, which is Memcached. This piece of software is essentially a database. It's frequently used by web developers. It's an in-memory key value store, which can be used to put and then retrieve values for different keys specified. So it's often used as a fast cache, hence the name. Long time ago, Memcached authors made a huge mistake. They made Memcache listen on all interfaces, including externally facing ones, by default. There are a lot of machines on the internet with port 11211 UDP open, and this port is Memcache ASCII protocol listener. This basic ASCII protocol was meant to be used on loopback interface only, or in a local secure network at most. Hence, it doesn't do any authentication, and it's UDP-based. And this weakness is known for long. 4 years ago, Ivan Novikov from Walarm has discovered numerous methods to exploit Memcached ASCII protocol to inject an arbitrary data in a memory of a Memcache instance. I can point you to his talk on Black Hat United States. And in November 2017, a new threat emerged. Security researchers Shangbao Kai, Zhang Liu, and Li Fu have discovered a way for an attacker to use the ASCII protocol to send large portions of data from Memcache memory towards a victim. Here's how it works. This Python code snippet is all you should do to inject an arbitrary value into a memory of a remote vulnerable Memcached server, here by the name reflector.example.com. The value may be of an arbitrary size. For the sake of DDoS amplification, this snippet should be run only once for each vulnerable server, of course. Then an attacker needs to send packets toward that vulnerable server with victim's IP source address and a proper payload, which Memcached will treat as a correct request. Here's how the payload is structured. This is, again, all an attacker needs to do to send a large portion of data they have put before under the key A. The value is reusable. Moreover, what's even more convenient for web developers, the gets method accepts multiple arguments. So here's what you can do to send the value 5 times in a row, multiplying the attack traffic 5 times, or 10 times, or 100 times. Our previous champion in terms of amplification factor was network time protocol, with amplification factor as high as 557, according to USCART. Other protocols carried much lower amplification factor values. For the Memcached amplification, in theory, the factor would be like millions, not billions because of the size of the initial packet, but still millions. Luckily, in practice, all the packets of the response aren't sent at once. In practice, we've seen an amplification factor close to 9 or 10,000. This is still 20 times our previous champion NTP amplification does. Seeing Memcached incidents in February, ranging between some hundreds of gigabits per second, we decided that in a network with a different architecture, we might expect more, up to maybe 1.5 terabit per second. What actually happened is 1.7 terabits. What contributes a lot to the problem is that in some Linux distros focused mostly on keeping backward compatibility, package maintainers are hesitant or reluctant to fix the vulnerability via distro-specific patches. Like in Red Hat Enterprise Linux, Memcached listens on all network interfaces by default. Both TCP and UDP transports are enabled, and no authentication is present. IP tables in Red Hat Enterprise Linux is supposed to take care of Memcached. This is sort of unfortunate, because users often expect a popular software to be secure by default, without any IP tables, NF tables, or whatever Bobby tables you are going to configure. Also, other dependent software like Zimbra is also doing the same. So how to mitigate that? First of all, do not allow a spoofed traffic to pass through your network. There's not only BCP38 now, but also other initiatives currently being discussed in IETF, so please follow that. Make sure you don't run a vulnerable Memcached instance in your network. You can use firewalls or BGP flow spec to filter port 11211 UDP across the border of your networks, as it's highly unlikely there's any legitimate traffic coming to or from that port today. Or given network transparency and stuff and different laws, you can use, like this snippet was posted by Job Snyders from NTT. Here's a link on the bottom of the slide, and the slides are available on the NANOG website. Here's how you can rate limit, not dropping totally, but rate limiting amplification sensitive ports, including Memcached in Cisco IOS XR, using policy map, and here's the second slide. Like, I won't go deep into that. The slides are available on the meeting website. What I really wanted to talk about is What I'm going to do next time such a vulnerability is discovered. Because we know web development won't stop producing these, and say gaming industry won't stop either. It seems like high time we'll discuss that across the connectivity providers community, because like 1.5 years ago, we already experienced this. Remember all those frightening headlines on the news about the Internet of Things threat and a terabit DDoS? Ironically, that happened a couple months after the TechSec working group in RIPE concluded. So numerous other working groups were launched to address specifically the problem of Internet of Things security. It's now 1.7 terabit, which is almost 1.7 times more than the Mirai attacks. And Memcached is not IoT. Should we expect a Memcached working group now? I don't think so. It took 3 months for Memcached to go from the disclosure to the actual threat. 3 months are an overly short interval. And we have an even better example here, the Cisco Smart Install vulnerabilities, which got exploited a couple of weeks after they were patched and security advisories were successfully published. We can make here some use of an embargo approach. That's when a vulnerability is first disclosed among a few organizations generally capable of fixing it. However, as Meltdown and Spectre show us, the embargo approach often doesn't work as expected for a community large enough. So maybe that's what we want to focus on, like collaboration and timely reaction across the providers community, or a security working group, or even better, a security incident response team capable of releasing a disaster recovery plan for us next time. Oh well, I've already proposed that during a RIPE meeting and got a sound objection. The issue here is that those CEIRT or CSIRT words were recently marketed too heavily, and so heavily that a lot of engineers don't want to hear those words anymore. Okay, so there are only 2 hard things in computer science. That's cache invalidation, naming things, and off-by-1 errors. So I'm here not to picky about names. But what I propose to think about and talk about is coming up with something, some community or working group in some constituency, that in order for us that the next time we face something like that, we'll be ready to face it. So there's a context for me, but I will prefer to have this slide during the questions and answers, and we can start with those. Thank you. Any questions?
Oh, we have a microphone this time. Matt Petak from Oath. So you said you brought up the CERT idea and got shot down in one particular forum. I would say don't let yourself be discouraged because one forum was short-sighted and thought it was a bad idea. I do think with the increasing number of incidents we're seeing like this, it really is high time we get a group of us together to say, okay, let's get a more coordinated approach. 1.7 terabits, not that big, but it's not chump change. We really should take these a little more seriously. If you're looking for what constituency, I think everyone's pretty much agreed the internet is global at this point. I think it has to be sort of all constituencies, so to speak. We can get the effort started here, but
everyone's responsible means nobody's responsible. So,
but at the same time, we can't say, well, this is a U.S. only effort or a Europe only effort or something like that. With DDoS attacks, there are no borders involved per se. So, I would be one to say, yes, let's get that CSIRT, let's get the working group going, let's make it happen. Don't take no for an answer. Let's keep pushing. Thank you.
Thank you for your feedback.
Joel Yegley. Actually, you're first. Okay. So I think one of the interesting properties of this is that it's not very useful if this information is secret. Like these particular kinds of attractive nuisance live in data centers, and they're those things are all over the place, but they're actually relatively concentrated, which is like with this particular kind of attack versus, say, you having a bad resolver on some kind of CPE, in which case there might be millions of them out there. There were never millions of these things. There were only thousands of these things. They were in locations that are relatively easy to identify. Obviously, they cannot spoof their own source IP addresses. The fact that some of these things still exist is a bit of a mystery to me. But like, as a community, I think we are better off if we share this information more widely and quickly than if we try and hide it.
Don Smith, CenturyLink. You mentioned flow spec and ICMP and fixed ports, and I didn't quite understand what you were trying to say about flow spec, ICMP, and ports.
No. That's two different issues. First of them is ICMP amplification. The second one is UDP-based protocols, EDP-based amplification, without a fixed port. The simplest example is BitTorrent. But I've just came up with a more complex example like WordPress, which isn't even UDP-based. So that's two different issues. First of them is ICMP amplification, which doesn't have anything to do with ports, of course. There's no ports in ICMP. And the other issue is amplification without a fixed source port.
Right. While there are no ports in ICMP, FlowSpec does support code and mode. So you do the same thing with ICMP you do with TCP or UDP. You just don't call them ports. It supports it, I promise you. The next thing is, if you dropped...
Let's discuss it later.
If you dropped all UDP 112.112.1.1 with a size of 1028, this attack ended. The attack was over as soon as you did that.
Yes, in this case, for Memcached, yes, this works. I've told that, I've put that on the slide with mitigation. The idea is that flow spec is still no silver bullet, so next time it might not help. We don't know.
Rafał Szarecki, Juniper Networks. Thank you for bringing these fixed ports. Some attacks are from fixed ports, that's true. Some they are, but the question is, for example, this Memcached 11.2.11. Can we blindly block this port? This is it's registered port, not the standard port.
Yes, of course.
Which means that other application may use this port.
Yes, it is.
So if I'm owner of my network and I block my devices, fine, because I know what I'm doing.
Yes.
But as a service operator, can I blindly drop all these ports? This port and say, hey.
Yes, there's a trade-off. I mean, I'm not saying it's impossible for a legitimate traffic to come to or from this port. I'd say it's highly unlikely. So, in case you're facing a large attack of that sort, you don't actually have a trade-off. You don't have, you can't come up with a solution which is good for everybody. But most of the time, you can either rate limit this port or drop it if you are legally able to do that. But yes, this is not a 100% solution. This is just something you can do to like a disaster recovery scenario, nothing more than that.
So you're just saying that we can sacrifice something in
Yes.
better good, and I agree, and we can go even better. We can look into the payload,
Yes.
or look deeper into the packet,
Yes.
and say, hey, this is still this port, but it's not Memcached.
The funny thing is that it's still so.
I think we can stop here because this is your
yes.
call. Let's discuss it.
Yes,
So-
I mean, it doesn't have anything to do even with IANA allocation of the port, because different applications may even use ports officially allocated for other applications. So with like NTP amplification coming from a perfectly standard port, you'll still have the same sort of an issue, maybe to a lesser extent, but it's still theoretically possible, like with Memcached. So it's like a common problem.
So to inject, Barry Green from Akamai, if you've been around for a while, you know there's ports that we have on the internet that we have been filtering. So as we saw last year with MyPetra and WannaCry, exploitable port filters, or another phrase of that, infrastructure ACLs, which are ports that we say we're just not going to allow them inside or outside of an autonomous system. From an ISP perspective, you permanently filter them. And we saw geographic distribution that those regions in the world, especially the United States, who had over a decade did exploitable port filtering, they were more resilient to those sort of attacks we're scanning on these common ports. This particular attack vector may be qualified for it. So yes, you can, there's a paper that the CSIRT community, the ISPs, we wrote together and we published it out there, and you can look through that. Lots of operators publish what ports they filter, right? Comcast filters a port, Comcast filters the ports and says, here's what we filter. Sorry, you can't use these ports, because there's too much garbage on it, right? And this may be a qualified on it. Every now and then a port appears and we're gonna have to filter it. That's life. My
Thank you for that
comment to this is, this particular one with Memcached, as a industry issue, community stepped up and responded to it pretty quickly. I mean, this thing was hammered out and responded to very, very quickly because there are security
1.7.
operation forums that work together with that, right? So we got several different trust groups that work together. If your organization's not part of it, come see me. I can help you, vet your organization into these security operational groups. The first community, which is CERTs, right? They're meeting in Kuala Lumpur right now. They all stepped up. So we're doing pretty good coordination when these things pop up. I think the thing with this that you didn't point out was, one, exploitable port filtering is one of the mitigation techniques, not with FlowSpec. And the other one was, we knew this was going to happen. So the interesting thing about amplification attacks is we know they're going to hit us, right?
Yep.
We go through and do the protocol analysis. There's
Sure.
researchers that go through the protocol analysis. We knew about this 2 years ago, that somebody was going to exploit this, and yet people didn't do anything about it. And so that's the thing in there right now that we got to look at. So if you want to, like, for instance, look at the level of, on your organization, every autonomous system here, you can go to a place called www.cybergreen.net, right? And they will list out DOS reflection capability that your network can launch into the internet. In other words, a bad guy can use your network and reflect out of your network and attack somebody else at the volume size, right? So it's not that we don't know it's going to happen. We know it's going to happen, and we can identify it on your network, right? It's that nobody's doing anything about it until, pardon the English,
Yep.
stuff hits the fan.
May you introduce yourself once again, sorry? Or, okay, we'll have to have a chat later.
Yeah, Teddy Vandenberg, IBM. So talking about the mitigation is fine. This one was actually pretty easy to mitigate, and we were able to stop the attack really easily by cutting off the source. But the problem is the IP spoofing. So how bad does this have to get where we demand the vendors do something drastic, like it
Gus?
RPF by default?
Yep.
Something like that. We demand that everything that goes out, you have to know what you're turning off in order to allow IP spoofing to happen.
As I've said, there's Okay, BCP38 is with us for a decade or more than that. And I mean, and it's not implemented by a lot of ISPs. I mean, there are a lot of different approaches currently floating within different IETF working groups. Yeah, so maybe it's time to go into that and to help develop them. So maybe they are something you can use to actually solve the problem of spoofing. So, but we'll need to find a proper approach.
So what I get out of it is that I think everyone in here is using BCP38 for the most part, except for a
Can
few
you raise a
outliers.
hand if a BCP38 is working well on your network? It's not too much.
So there's not much
It's not
spoofing
too
source
much.
here. Like we have vulnerable stuff on our networks because it happens, but we're not the problem. All we can do is mitigate.
And that's even North America. I'm not talking even about developing
Well,
countries.
yes, I'll agree with you there. Thank you.
So I'm running out of time, so thank you very much for your questions.